In this video, we'll take a look at random forests. This will build on our other videos on where we looked at the decision trees, classification and regression trees, and we also talked about bagging or bootstrap aggregation, and we will combine both of those with also the method of random subspaces to obtain random forests. So random forests are extremely simple technique, and yet somehow they have essentially state-of-the-art performance. There was a study done, I'll just cite Caruana and Niculescu Mițel, I'm probably butchering that, 2006. They compared a large number of 10 different binary classification methods on 11 different data sets and compared them using 8 different performance metrics. Essentially, so the results were random forests came in second, topped only by boosted decision trees. So we haven't talked about boosting. Boosting is another aggregation technique. So, and third was bagged decision trees. So we talked about bagging and decision trees, and if you bag decision trees, you get bagged decision trees. That came in third. SVM was fourth. So essentially, and then down the line, neural networks, and then they compared a bunch of other stuff to just logistic regression, naive Bayes, but basically random forests were all the aggregated tree methods were at the top. So that's a very interesting fact. So what is random forest? How does this work? So I'll just outline the algorithm. It's very simple. So we have, as usual, in the supervised setup, we've got these observed data points, some sequence of x's and y's, and let's call that D. And the algorithm is, so for I, as I goes from 1 to b, for some number b, we're going to construct b trees. And for each tree, we'll do it in the following way. So we choose a bootstrap subsample, a bootstrap sample from D. Call it di from D. And this is just like what we talked about bagging. You just sample n points with replacement uniformly from this set. And then using di, we construct tree ti using di, and we modify our previous tree growing procedure in the following way. And we do it by such that at each node, so at each node, we're going to choose a random subset of the features. Choose a random subset of features. And we'll consider only splits on those features that would split those features. And only consider splitting on those features. So on that subset, features from that subset. So we would choose, say, this is some number, we'll have, say, m. Say we'll pick m features, and m is so there's 2 parameters here. B is going to be our number of trees, and m is going to be the number of features. And here, so if the x's were, these are, each xi is a point, say it's an RD, for example, or more generally just d-dimensional. It might have categorical inputs. So let's say xi is d-dimensional. So m is some number less or equal to d. Usually we want it, less than d. D might be very large, and m could be rather small. So we're going to choose this, we'll choose some for each node, we choose some subset of features, and when we are considering all the possible splits, we're looking for the best split at that node. We will only search over that subset of features. So this is what's called a random subspace. So this subset of features defines some subspace of this d-dimensional space. So this is the random subspace thing. Subspace. So we do this at each node. We follow our usual. Otherwise, we follow our usual tree construction procedure, and we get tree ti. And at the end, so after all this, we just do the usual aggregation thing. So we've constructed all these trees, and then for our aggregated predictors, we would say, take a majority vote, given a new X to classify, take a majority vote over these B, over these B trees, T1 through TB. Or you could, if you were doing regression, so this would be majority vote for classification, or you could average the probabilities, or just average, or generally for regression. So that's a very, very simple algorithm, just essentially repeating the decision tree construction, and what makes this work is essentially it's the same reason that the bootstrap aggregation works. The problem with using an individual tree is that it has high variance. It's very sensitive to the particular arrangement of the data points, and you might get unlucky. And so each individual tree has high variance, but by averaging over an ensemble of trees, that's what these methods are also called ensemble methods, aggregation methods. So averaging over an ensemble of trees, you can reduce the variance of the overall final estimator. And therefore, you can reduce, so we'll see in from the bias variance trade-off, the bias variance characterization of performance of a classification or regression or estimator in general, that reducing the variance can lower your, well, in general it will lower your performance. I mean, it will increase your performance. It will lower your error. So that's it. That's random forests. Random forests. Oh, so random forests were introduced, I should make clear, by Breiman. Also introduced the classification and regression trees. So Breiman introduced a lot of very useful models, a very famous probabilist, or statistician, I should say.